In this lesson, we relate the potential gradient and the field strength. Here are the objectives. Let's start by looking at a simulation. This is a simulation from O-Physics. It's the same one we used in the previous lesson. And I've got a central positive charge with equipotentials shown in green around it. I've reduced the charge on Q2 over here to 0, so this is actually not here at all. And you can see that I have a sensor that's measuring potential and electric field strength. And as I get that sensor closer to the central positive charge, both of those go up. The potential increases as I move to ever higher areas of potential as I cross equipotential lines, and the electric field strength, as indicated both by this number and by the length of this vector arrow, goes up as well. Now, if I change to the three-dimensional view, remember that height is a good analogy for potential. As I get to higher and higher potentials close to the central positive charge, it's like I'm moving to higher and higher heights. So you can see then that as I move the sensor closer, and I get to areas where the potential lines, the equipotentials, are bunched closer together, I'm moving to steeper parts of the graph and the electric field strength is getting greater. So steeper parts of this graph, in other words where the equipotentials are closer together, are areas where the electric field strength is greater. Those two things go hand in hand. Putting that into words, at any point the field strength is given by the magnitude of the potential gradient. And by potential gradient, we mean the gradient that we saw in that red graph. The potential gradient is the slope of a potential versus distance graph. And that's what we got a visual of in that red topographical map. Here I've made the central charge negative now, but it's the same kind of thing. As I move my sensor closer and I get to places where the equipotentials are bunched closer together, what I'm doing is moving to steeper parts of this graph down in this well, and as a result, the field strength, as indicated by the length of this arrow, is getting greater. If I now draw that topographical map in profile, then what I'm doing is I'm graphing potential versus distance from that central charge. And so I'd see something that looks like this. Again, it's like a cross-section through the topographical map we just looked at. And I can put some numbers on here. I'll just make some up. So let's say that's negative 10 volts, negative 20 volts, negative 30 volts, negative 40 volts. And so our central negative charge would be somewhere over here at r is equal to 0. And now you can imagine that these become our equipotential lines, these dotted lines that I'm drawing. And if you were to look down on this from above, down on it like this, you would see these ones here bunched closer together where the graph is steepest. And that's really what we were doing in the simulation when we toggled between the two views. Now, as we saw, where the graph is steepest, the electric field strength was greatest. So here, if I look at the slope of the graph over here, it's greater than the slope of the graph over here. And that means that here, the electric field strength is stronger than it is here. So let's call this E1 and this E2 for the electric field strength here and here. E1 would be greater than E2. The arrow in the simulation would be longer at the steeper parts of the graph, the arrow showing the electric field strength. Now the slope of those lines, the rise over the run, is the change in the potential divided by the change in the distance from the central charge, or delta V over delta R. Although in calculus, we'd actually shrink these distances down infinitely small, so we got a tangent instead of a secant, and so really you'd see dV over dr. The d's instead of the deltas, meaning the distances along the y and x directions are infinitely small. So this notation means the slope of these tangent lines to the V versus R graph. But you'll see this in the formula booklet. So the electric field strength, the magnitude of the electric field, is given by the slope of that line above, the V versus R graph. And I say the magnitude because there's actually a negative out front here, and that is an indication of the direction of the electric field. I could put a little E here to indicate that we're talking about the electric potential. Similarly, for the gravitational situation, it's the slope of the potential versus distance graph for the gravitational situation. So these are just ways of saying in formulas that the field strength is given by the magnitude of the potential gradient. The potential gradient being these slopes above that we saw on the V versus R graph. Now let's use that formula to look at a special case, that of a parallel plate capacitor. So if this is a parallel plate capacitor with positive charges up here and negative charges down here, and my field lines are going to point downwards, then we know that the field is uniform. That means that the equipotentials are equally spaced. So if this is at 0 volts and let's say this is at 100 volts, then 50 volts would be here in the middle, and we'd have a 75 volt equipotential here and a 25 volt equipotential here. So if I were to draw the graph of the potential against the distance from the top plate, we'll call that R, then I would have 100 volts here. This is my potential, and I'll put 50 volts there, and I'm going to get a straight line with a negative slope like that. And the magnitude of this slope, delta V over delta R, and I'll put absolute value brackets around to show I just mean the magnitude, is going to give me the magnitude of my electric field by this relationship up here. Well, the magnitude of that slope is just the rise, which is 100 volts, divided by the run. And the run here is whatever the separation of the two plates is. Let's say that the separation is 0.5 meters. Then the magnitude of our electric field would be equal to the magnitude of the slope, and that's equal to 100 volts divided by 0.5 meters, which gives me 200 volts per meter. And working out the units, because a volt is a joule per coulomb and a joule is a newton times a meter, this works out to be the same thing as 200 newtons per coulomb. More generally, the magnitude of the electric field strength, is equal to the potential difference between the two plates of a parallel plate capacitor divided by the separation of the two plates, which I'm indicating here by D. So in our example, D was equal to half a meter. So in this lesson, we've looked at how the field strength is given by the magnitude of the potential gradient, the slope of the V versus R graph, and we've also looked at the special example of the parallel plate capacitor.